Chapter 4, Heat Engines and Refrigerators. Here's the overview of the chapter. 1, we want to use the second law of thermodynamics, which is about entropy, to understand how interacting systems come to thermal equilibrium. 2, we want to analyze heat engines and their energy transfer diagrams. 3, understand the significance of a Carnot and an engine efficiencies. And then finally, we want to analyze refrigerators and its coefficient of performance. So this lecture is going to be on irreversible, reversible, and equilibrium. To distinguish what is irreversible versus reversible, let's start by looking at this heat interaction. So what we're going to do here is that we're going to compare two heat interactions. I'm going to have a container. Let's say that it's like this. And then I'm going to have a separate container. So in this situation, this is going to be a cold region. That is a cold gas region. Whereas over here, this is going to be our hot region. And we're going to let these two interact with each other. So this is the hot, and then, of course, this is the cold gas. And what we're seeing here is, what I'm saying here is that I know that this is temperature 1, and this temperature is, of course, proportional to the RMS kinetic energy. And we're going to say here that this has some internal energy initially that looks something like that. So I could say the exact same thing about the cold region, where the temperature and the kinetic energy are proportional to each other, and then this will be the internal energy of this. So the way it stands, T1 is greater than T2, which immediately tells me that K RMS 1 has to be higher than K RMS 2. Now what we're going to find here is that the system always moves from high to low kinetic energy. So when I look at this thing, what do I find? Well, if they interact, what we're going to see here is that they're going to reach thermal equilibrium. So what do we mean by thermal equilibrium? Well, their temperatures, or the KRMS, are now the same. So that means both of these now have the same temperature. And so that means here that TF, which is now proportional to this, and then this has the exact same KRMS values. And then, of course, this has some final internal energy, and this also has some final internal energy. So what we mean by this is that T1 final is the same as T2 final, which I've just written down as TF. And now if I look at these containers, I see that KRMS1 is equal to KRMS2, even though they're different gases. Now the internal energy is going to be a little bit trickier. So if N2 is greater than N1, then that implies here is that the final internal energy of 2 will then be higher than the internal energy of 1. On the other hand, if these two are equal, then their internal energies will be exactly the same. So we all know that energy is transferred from the hot to the cold gas. So now this begs the question, why does it not spontaneously move from the cold, which is then low kinetic energy, to the hot, which is high kinetic energy region? Why does it move from the hot to the cold? That is, why doesn't the cold get me? I should write this. That is, why doesn't the cold gas get colder while the hot gas gets hotter? During a heat interaction. Why? I mean, we can sort of like, I mean, if you think about this, it's sort of something like this here. So this is, we experience this. And what I mean by this is that if I have a hot cup of tea, okay, and then what we'll see here is that the heat radiates outwards. This is what our experience shows, and it radiates out to the cold air. Right? That's what we see as heat transfer. We never experience experience a cold cup of tea get hotter all by itself. So if I think about this, I start off with a cup of tea that now is cold. And so if I have room temperature, where this is now cool air, why does heat not come from the cool air in this direction and reheat the cup of tea, right? So when we talk about heat transfer, this never occurs. So now that I set this up, we see that this does not spontaneously happen all by itself, right? So this process, this does not occur spontaneously. Like we could put it into a microwave and we could heat it up, but that's not all by itself. The crazy part about this forbidden process is that this does not violate conservation of energy. So, according to conservation of energy, this process is possible, but it doesn't occur. It never occurs. In irreversible, process is one that can only occur in one direction. Like this cup of, cold water getting colder doesn't happen, but a cup of hot tea cooling off does happen. That's a one-dimensional process. That is, the cup of tea always cools down and never gets hotter by itself. This is one directional. So now that we kind of set this up, so now I want to look at examples. Now note that there's lots of examples, but here are I'll say that here are two clear examples of irreversible. So the first one here is that if you're stirring creamer into your coffee and mixes well, no amount of stirring will ever unmix the coffee and creamer. No amount of stirring will then have the creamer all get back together. And so you see this white dot. We know that is impossible. That's what I mean by irreversible. Another one is that consider a jar of red and green marbles. Okay, so if I look at that, what am I seeing here? Ooh, that's not right. So what I'm seeing here is that I have a container of marbles like this. And what I'm going to do here is that I'm going to separate the red marbles from the green marbles. And now what I'm going to do is that I'm going to shake this jar. And so what happens here is that I'm now going to have a situation where they get mixed up. Just doing random dots here. So let's say that then these will be red. So now I have a jar of marbles that start separated. So shaking the jar until the red and green marbles will never, how do I say this? Okay, so shaking the jar until the red and green marbles unmix. Will never occur. Right? So I have the reds up at the top and the greens, it just doesn't occur. No amount of shaking will unmix these marbles. No amount of shaking. It is impossible. So these processes are clearly irreversible, since they only occur in one direction. So now what I want to do here is that we can define better what's irreversible with the movie. So another way to describe irreversible is watching a movie run backwards. And it turns out that this is the way that I'm going to really look at whether something is reversible or not. So watching a movie run backwards will show a physically impossible in a physically impossible process. Here's one. Okay, let's see how my artwork does. So I'm going to have a car crashing into a wall. So I look at my car and it goes like this. So my car's here. And let's color my car. And what I'm going to have here is that this is going to be the driver of the car. And what we're seeing here is that this guy is now going to crash into a wall. So we know that in this direction, this is the direction of time. Okay, so time goes like this. So now what's going to happen here is that I'm going to see something like this. So then the car crashes into the wall. And what we're seeing here is that now the car has now smashed into the wall. And then this person, well, I guess has died in the car crash. So this is a frontward running movie. And, I should say this is the direction of time. So I'm going to make this a little bit bigger. Now, if we were to run this thing backwards, right? So if we were to run this backwards, and so now if I have the exact same situation, so let's say I copy this, and then I paste it right here, but now this is a backwards running movie where now you see that the time is going like this instead. So this is now the direction of time. I mean, if you look at this, we immediately say that obviously, something is very wrong. So by looking at this thing, I can then say that we could then say if a movie was made of this process and runs backwards, it clearly shows a physically impossible process. So we can say here is that irreversible processes show a clear distinction between past and future. This is what happens at the macroscopic scale. So what we say here is that these processes are overwhelmingly irreversible. So now that we hopefully have a clear picture of what we mean by irreversible, now let's talk about reversible processes. Reversible processes can happen in both directions. And a backwards running movie shows a physically possible process. So here we go. What we know here is that interactions at the molecular level, you know what? I think I'm going to make that big. At the molecular scale, are reversible. As an example, so we're going to have a collision between two gas particles. So in this case, I'm going to have a frontwards running movie. And we could imagine here is that I have a red gas particle coming in, and then I have a green gas particle coming in. And this represents the before. Now they collide. And so as they collide, what I'm going to see here is that this guy, let's say, moves downwards in this direction. And then the green one that started here now moves upwards. So this is the after. But now let's run this backwards. So now if I have a backwards movie, then I could imagine that I have this scenario. So if I run this backwards, it looks like this guy is now going to be doing the opposite. And so this is the before. And then afterwards, we're then seeing that the process looks like this. So it starts off here, and then this one goes in that direction. And this other one starts off here, and then this one goes in this direction. So here's what you show. So a movie of this process shows that it's clearly possible. So what we're seeing here that in this case, you cannot tell which are going forwards or backwards. Nothing looks wrong. So then interactions at the microscopic scale are reversible processes. So how do I say this here? As stated earlier, collisions between gas particles look okay, while cars crashing into walls do not violate any laws of nature. So I should probably write this. So looking at a backwards movie does not show any impossibility. That's a definition of reversible. So now from our examples, I'm going to say here that collisions between gas particles, and again, this looks okay in a backwards running movie versus cars crashing into walls. So in this situation, does not look okay with a backwards running movie. So this presents a paradox. And the reason why it presents a paradox is that in science, many people state that macroscopic phenomena can be understood on the basis of molecular motions. Clearly, this is not true, right? Clearly, this is not true because we can see that something happens. So if I was to now summarize what we just said here, we then say that microscopic motions are reversible, while macroscopic motions are irreversible. Overwhelmingly. So this is what I've been trying to show here so far. So again, for example, so if we now bring this to thermodynamics, so a thermal example, this tells us that heat transfer from a hot to a cold gas is irreversible, but the molecular gas collisions in this process are reversible. So then we have, because there's two separate things, we now have an important question to ask. What is violated in the backwards running movie of irreversible processes. That's not violated at the macroscopic. We can say here is that up to this point, no laws. And when I say laws, I could talk about energy, momentum, whatever you want to talk about, are violated, but irreversible process cannot go both ways. And what I'm asking is, why is that? Right? Why is that? So there must be another law of physics from preventing this. Preventing it that distinguishes between past from the future. So it's really the same question that we talked about before when we started this lecture. So if I go back to a thermal interaction, what law prevents the transfer of heat from the cold to the hot gas? That's the question that we're asking right there. So now let's try to answer this thing. And this here, I'm going to call this the large number effect, and which way to equilibrium. So let's go back to the marble. So how do I say this here? So let me repose the same question that we started with. What law prevents the transfer of heat from a cold to a hot gas? That was the question that we always talked about. So now I'm going to pose the second question. How do two systems initially at different temperatures know which way to equilibrium. It's the same question, just slightly different. So what I'm going to do here is that I'm going to consider a much simpler example. And what I'm going to do here is that I'm going to go back to the red and green marbles. Okay, so let's go back to that example, but it's going to be slightly different here. So what I'm going to have here is that I'm going to have 2 containers of marbles. So let's say that I have this container. And then I have the exact same container filled with green marbles. So what I'm going to do here is that I'm going to label this container number 1, and this is container number 2. So I'm going to copy this because I want to look at what happens afterwards. So here I go. So now I have my containers fixed. And what I'm going to have here is that I'm going to have red marbles in 1. So let's say I have, I don't know, just some random number of marbles like this. And so this number here is the number n, the number of container initially. Now I'm going to have a green container of marbles that looks something like that. And so when I look at this, this is the initial number of the green. And clearly, this guy is larger. Now, what am I going to do here? What I'm going to do here is that now I'm going to make numerous moves from here. So that means I'm going to take a marble and I'm going to move it to container 2. And then I'll take a marble from container 2 and I'll move it to container 1. So what happens here? So suppose every second, 1 marble is randomly moved from jar number 1 to jar number 2. Because N1 is greater than N2 initial, there is a higher probability that more marbles, more red marbles will be moved than green ones. Just because they have more. And if it's a random process, it has to do that. So after some time, the jars will evolve where the final number of the reds is approximately equal to the final of the two. So if I look at this thing, I'm now going to have, let's say, some mixing. So let's say that I'm going to have this, and then these red marbles, I don't know, whatever combination that we want to look at. I'm not counting the marbles, but you're seeing here that the final number here of one final and the final number of two, that these guys are approximately the same. So I would say that this is a stable system because no amount of movement will ever separate the red and green marbles as in their initial state. So in other words, when I say the word stable system, this is the same word as equilibrium. So when we look into thermodynamics, this is effectively what happens. So now, if I just make some observations about this, here's what we could say. So here's two remarks or observation. One, I would say that when a marble is moved between jars, these are reversible because a backwards running movie is physically possible. Two, if one started unmixing the red and green marbles, what do I mean by that? One container gets more red while the other one gets more green. A backwards running movie would show an unphysical possibility. And that's what we mean by irreversible. So now the question is, how does the large number comes in now? So maybe I should say, what does this have to do with large numbers? So what I'll do here is that I'm gonna, let's use an analogy. So we're gonna be tossing coins. And we all know that if you toss coins, they say you have a 50-50% chance of getting heads or tails. So we can say here is that a tossed coin has a 50% chance of landing heads. So let's talk about heads. So here we go. So now what we're going to do here is that we're going to toss, we're going to throw 4 coins. So then, what are the odds of getting all heads? Well, here's what you find here. So if I look at, so from statistics, I'm going to throw 4 coins. So then what we find here is that the probability, if it's 50%, then it's 0.5, right? That's 50%. And then to the power of the 4, because I'm tossing 4 coins, this tells you that you get 1, and so 1 toss out of 16 throws, you're going to get 4 heads. So that's effectively around, I don't know, what is that? Like, that's around 5%. Okay, it's a little bit more than 5%. There you go. That's the probability. So now, what happens if I do this? What happens if I throw 10 coins? Then what we say here is that the probability of all heads now goes from 0.50 to the 10th. What are the chances of you getting all head? It turns out to be 1 in 1,000 throws. So it's getting much harder to get, all heads. And then we can continue and go like, what happens if I throw 100 coins? What is the probability of all heads? And what you'll see here is that now it's 0.50 to the 100. And now you got a chance of 1 in 10 to the 30. In other words, you're gonna have to do an awful lot of throws to get 100 coins. Now, if I go back to my green and marble example, as the number of red and green marbles increase or increases. And if we talk about atoms in a gas, what if those marbles were gas atoms and we're talking 10 to the 20? The odds of even finding most of the red marbles in jar number 1 is so staggeringly small, it will never happen. So in summary, a thermal system reaches thermal equilibrium not by any plan or outside intervention, but simply because equilibrium is the most probable state in which to be in.